You have the speaker on. Eleonora.
I think so.
Because you have to record.
Yes.
You can hear me, right?
Yes. Okay. Good morning, everybody. Welcome again for this new colloquia at the Istituto de Astrofisica Andalucía. And today we have the talk by Eleonora Fiorellino from the Osservatorio Astronomico Capodimonte in Napoli, but she's a postdoc in Rome now. And she will talk about measuring accretional rate on class 1 protostars. So Eleonora will be introduced by Isabel.
Hello, good morning, everybody. Thank you very much for coming again to a new Severo colloquium. So thanks a lot. And first of all, thanks to our speaker today, Dr. Eleonora Fiorellino. Thank you very much for having accepted our invitation to this program from the Severo Excellence Award at the IAA. Eleonora Fiorellino is since 2022 postdoctoral fellow at INAF, as René said, at the Osservatorio Astronomico Capodimonte in Napoli, under the PRIN project straight with the INAF-JEDI collaboration. She was born in Rome and she studied at the Università degli Studi di Roma, La Sapienza, and graduating for the bachelor in physics in 2014 and the master in physics and astrophysics in 2017. She won a scholarship at the Rome PhD program in astronomy, astrophysics, and space science, hosted by the Star Formation Group of the INAF Istituto di Astrofisica, Planetologia, Spaziali, and INAF Osservatorio Astronomico di Roma. During her PhD, she obtained an EXO studentship in Garhin. She defended her PhD thesis during COVID, so that's extra points, I guess, the 23rd of December 2020, so a precious Christmas present for herself, I guess, about star formation from the pre-stellar course to the accretion of young stellar objects. She worked at Concolli Observatory in Hungary until 2022 under the ERC-funded position Sacred. And since her PhD, she studies how stars and planets form. And today, she will talk about the evolution of accretion processes, as you know. So thank you very much, Eleonora Fiorellino, and the floor is yours.
Thank you. Thanks a lot. Actually, thanks for inviting me. I hope you will enjoy this colloquium. So as been said before, I'm going to talk about how to measure the accretion rate, and I will focus on a particular stage, the class 1 stage. In order to justify this, let me do some not working. Amazing. Okay. Okay. Let me do some introduction. I'm sorry for the expert. Maybe this is boring, but it is what it is. So I'm going to focus on low mass stars. Let's define what we mean by low. Everything smaller, well, less massive than 2 solar masses. At the very beginning, we are interested in the so-called protostellar phase. So at this stage, the objects that we study are just made of gas and dust. So there is no star here. And the LCD distribution looks like that. So we can study that in the sub-millimeter. This stage is important because according to the current star formation scenario, when these objects are enough self-gravitating, they can collapse. They can collapse, producing actual protostars. And what we mean by the protostellar phase is actually class 0 and class 1 objects. During this stage, there is a forming star where the hydrogen burning is not there at all, but still there is gas and dust with a certain temperature, but everything is surrounded by a dusty envelope and circumstellar disk. At the class 0 stage, the envelope is so thick that we cannot see through it. So we cannot see either the photosphere of the forming object or the disk. And then by the time this envelope dissipates, and during the class 1s, we start seeing both the circumstellar disk and some contribution also of the forming star. However, the situation is still a lot complicated, as you can see from the XCD. And it's only during the priming sequence stars, composed by the class 2 and the class 3, then the envelope basically is all dissipated, and you can study in detail the circumstellar disk and also the photosphere of the forming star. The class 3 is defined as the very last stage where the deuterium burning occurs into the star right before the main sequence stage. Okay, so this scenario that I just described is very not efficiency. If we study how much material there is during the protostellar phase, and then we compare it with the mass that we observe in mid-sequence phase, we've got this number. So 0.2, 0.4. There are several ways but to do this. I will show you just this plot just to give you an idea on how this is computed. So in the black, you can see the initial mass function, so the statistical mass distribution of main sequence stars. And in the blue, the core mass function, the statistical mass distribution of protostellar cores. This is an example for serpent star forming region, but you can see there list a lot of similar studies. And in all the cases, what we get is that during the star formation process, more than half of the protostellar core masses do not contribute to the main sequence stars. So the key message here is that the star formation, like core collapse, is not efficient and is not efficient mode to form star, and is also like not by only this that the stars gain all their mass. So the question comes naturally: how stars collect their mass? What's happened during the stages that I listed before? There are several theories, and for the moment, the ones that we like the most, because it's more or less what magnetospheric accretion scenario. So according to this scenario, from the material from the envelope arrives into the circumstellar disk. It arrives onto the outer part of the circumstellar disk, and then it reaches the inner part. There are question marks here because we at the moment we don't know what is the physical mechanism that drives this migration of the material from the outer part to the inner part. The point is that when the gas and dust is in the inner part of the disk, it encounters the magnetic field lines of the forming object, and by following them, it shocks into the central object, accreting its mass. Now, all of this is happening while the star is rotating. And as you know, in order to conserve the angular momentum, if something is accreting the young stellar object, thought as the composition of both the forming star, the disk, and the envelope, something should should be ejected as well. And there are some indeed winds and jets. But the point is that all of this is happening at scales of about the astronomical units. And it's very challenging to see this directly from imaging and even from interferometry. Now with ALMA, we're starting doing something with very close objects, but in general, if you want a physical approach, you need to use different techniques. And the spectroscopy is the most useful technique for these things. This is why we love it so much. Okay, so if you got a question for the moment, and don't mind being interrupted. Okay, if everything is fine, just go ahead. I need to define some parameters. The first one is the veiling. I will talk about it, and it is defined as the ratio between the infrared flux and the flux of the stellar object. And it defines how much veiled is the forming star because of all the accretion properties of the young stellar object. And then we do have the mass accretion rate, So literally how much mass is accreting per year onto the forming star. And this is the equation. So basically you need the luminosity due to the accretion luminosity, and the stellar perimeter of the stars. Then we have to know that the physics which regulate the disks, as I said before, well, is not completely understood, but we know that it's like the viscosity and the winds play an important key role on this. And lastly, the evolution of all the young stars is composed not only on the evolution of the stellar mass, but it's an interplay between the mass accretion rate, the disk mass, and the envelope mass. So I will start with the mass accretion rate, and in particular with simulation. So observationally speaking, this field is very challenging, but since 2000, there are several simulations. This is the one by Albert, which showed you that basically, so this is the mass accretion rate as a function of the age. So it shows how the mass accretion rate should evolve under a theoretical point of view. And you can appreciate here the steady part of the equation. Okay, so this region here, and there are several works, and in particular the recent 57 chapter by Manara 2023 and Pineda 2023 that describes this mass accretion a lot. And this has been like demonstrated observational for the T-Tauri part star, and it's working. Then we do have also the so-called eruptive accretion. Here you can see some bursts that deviates from the steady part, and objects as EXors and FUor bursts are the classical objects that experience this strong, really strong eruptive accretion due to probably the instability of the disk. Again, if you are interested in this, there is a lot of literature here. Okay, now we will focus our attention on the accretion in class 1 and class 2. Okay, why is like that? Because for the moment we are able to determine the mass accretion rate only for these two stages. As I said before, the class 3, there basically there is no accretion anymore. It's just a really short phase when the system is preparing to do the hydrogen burning. And about the class 0 stage, so the previous one, it's so embedded that we cannot see the photosphere. So for the class 2, everything is well known. In here, you can see, I mean, I just point here all the papers that investigate the search, and you can see that there is a lot of literature. And I also wanted to show you this plot with so many regions where we've done this kind of analysis. Here you can see the mass accretion rate as a function of the stellar mass, and you can see that different regions more or less show the same behavior with a lot of spread. And if you've got questions about the spread, you can ask me. But then there is not only the study of the mass accretion rate as a function of the stellar mass, there is also the study of the mass accretion rate as a function of this mass. And you can see that there is a relationship again also with these two quantities, which makes sense, right? Because according to the scenario that we built, there is some material from the envelope arriving to the disk, but then it's from the disk, then it impacts on the forming star. So we could expect that the more massive it is disk, and the more material could it create onto the forming star. And then there is, okay, the question, why is like that? What is the physical mechanism that describe this scenario? We do have data for the class 2 sources. Yeah, the problem is that the data are in agreement with all the models that we got. In particular, here you can see the viscous model trend. Here, different colors relate to different regions, depending on their age, and also the MSD winds prediction and the dust of forming planets. And you can see that all the three of them could explain this, the data that we have, because of the spread and also because of the fact that we are not looking at here, for example, where the, for example, the viscous model is supposed to decrease a lot, while the MSD winds is supposed to be constant. And we also don't only have one region with very cold, okay? For us, very cold is like more than 5 megayears. Okay, so, but coming back to the previous slides, to the evolution according to the models, we've seen that we are focusing on this region, on classical Ptah stars. But then, like most of the mass accretion rate, according to the simulation, should happen before, in the protostellar stage. So while we spend a lot of time investigating the mass accretion rate, here, when we know, at least because of the models, that should be like faint a little, because it's easy, because it is what we can do, because classical Ptah stars emit in the visible and UVB wavelength, and life is less complicated in that wavelength range, as you know, and also because like the accretion tracers emit like are in that wavelength range. So here you can see an example. This is an exutor spectrum of a classical Ptah star in lupus, and I marked all the accretion tracers with respect the like different region on the young stars. So you can see that the UV excess, which is what like gives you how much luminosity, how much material is accreting onto the star, is here. Okay. And in the case of a classical Ptah star, you can see this. It is not, this part of the spectrum is not covered by the dust. It is not covered by the envelope or the disk. And then you can see all the Barnum lines, the Paschen lines, the bracket lines, in general, or all H lines in young stars traces the accretion and gives you information on the accretion. And then there are also, I mean, winds jet, forbidden hydrogen and iron, and the CO. You can also see the near-infrared excess here. And this is important because, I mean, in the dashed black line corresponds to the protostellar photosphere. If you do have the visible and ultraviolet spectrum, you can study directly the photosphere. But if you have only the near-infrared part of the spectrum, you don't see the stellar photosphere because of the near-infrared excess. Okay. Okay. Now, if this is clear, we can go around. I mean, this is just the recipe that we use for computing the mass accretion rate on classical Ptah star. It can be more or less challenging because of your data, because of your experience with routine, but we know how to do it. Yeah, but what about objects that we are not able to see in the visible or in the UVB? If you remember, an SED of a class 0 or even a class 1, like is veiled, is not possible to observe in UVB and visible. Okay, thanks to people like there is this work of Alcalá et al. 2017, but before them, the same group in 2014, and also Muserol et al. In 1998, try to determine these empirical relations between the accretion luminosity that we got directly from UV excess and near-infrared emission line. So here, for example, we're interested in the bracket gamma line because it's the most bright, is the brightest in the near-infrared part. And the idea is that we can use these empirical relations that works for classical Ptah stars to observe more embedded and we think also youngest objects, for example, class 1s. Okay. Okay. So this is what we've done basically. During my PhD, we developed this self-consistent method that uses the empirical variations aforementioned. The fact that the bolometric luminosity can be described as the direct sum between the accretion luminosity and the stellar luminosity. We said that a young star object has different components. So in the end, the bolometric, the overall luminosity of the objects is composed by several luminosities. The astronomical equation of the bolometric, where an important and key role is played by the veiling I introduced before. But still, we've got 3 equations and too many 3 parameters. So we need some assumption. And based on Spitzer timescales, we can say that those objects should have an age between the birth line. So the first locus when an object entered the EXors diagram, and 1 mega-year-old. According to Spitzer timescales, it's very unlikely that a protostar is older than 1 mega-year. This assumption could be even more precise, because in general, class 1 timescales are 0.5 mega-years, but we decided to be conservative because you never know. And this is what we get. So here you can say the mass accretion rate as a function of the stellar mass. So this is the exactly same plot that you've seen before, but this is only for NGC 1333, which is a very young cluster in cells. And in green, there are class 2s, so exactly as the plot I showed you before. And then in pink and black, the class 1s. First things to notice, the error bars, okay? For class 1s, we've got dots. For class 2, we've got dots. For class 1s, we've got bar. And mostly this is because of the assumption that we made here. So we can just provide a locus for each star, for each class 1s, that takes into account the possible stellar mass and accretion rate that the star could have. But still, it provides you something. It gives you an order of magnitude at least. And okay. And coming back to the famous plot, we can now we test this part of the plot. Okay. So we are quite satisfied about this because it's more or less in agreement with what the models suggest. But we've done this analysis only for 10 objects and only in a single cluster, in a single star forming region. We cannot generalize this, right? So the next step was to go for a statistical approach. And we selected 50 objects out of 110 known class 1s, for which it was possible to measure the veiling and to apply the self-consistent method I described before. And this is what we get. So here you can see the accretion luminosity as a function of the stellar luminosity. So this is different from what we've seen before, but it's however interesting because it tells you basically that those are class 2, and then here colored objects are different class 1 sample with different veiling, and the trend is the same for the less veiled sources, so the pink and red ones. But then if you study the more veiled sources, so the most obscured by the envelope, they deviate a little from the general trend you can see here. Okay? And so based on this, you should expect a similar behavior on the mass accretion rate. So more or less the class 2 will follow the class 1s, the red and pink will follow the class 2, and then the blue should deviate a little. This is not what we see. As you can see here, the class 1 is a very different population from the class 2. Of course, the error bars are quite large, and of course there are some assumptions on this, but the point is that what we know less here are the stellar mass and the stellar radius that plays an important role in computing the mass accretion rate from the stellar luminosity. And also there is an observational bias, because this is what we can do from ground-based facilities. So it means that we are only looking for the brightest class 1s, because we cannot see the most embedded sources. And also the most veiled show the same mass accretion rate of the less veiled. However, if we come back to the famous simulation, now we enlarged the mass accretion rate. So with more statistics, we were able to describe more or less all the protostellar phase. The problem here is that, well, the problem, we still are not able to cover the part, the strong mass accretion rate due to the eruptive event. All those objects are not known to being eruptively active. And the other point is that we base all of these on the Spitzer timescales. So under the assumption that the timescales of class 1s is 0.5 mega years, and in general not more than 1 mega year. But the idea is that if we just multiply the mass accretion rate for the time scale of this object, we should have more or less the distribution of main sequence stars, or at least framing sequence stars. This is not what we get. So the mass accretion rate of class 1s is higher of the mass accretion rate of class 2, but still is not high enough to explain their mass. And this leads to two possible solutions. Either most of the mass is already accreted in the most embedded phase that we are not able to observe, at least not from ground-based facilities, or that most of the mass is not accreted from steady accretion. It's just basically probably is due to this strong and not continuous eruptive accretion burst. It is a possibility. Okay, what we've done next, we studied the disk mass. You know that now with ALMA, we can provide, well, estimate of this mass, and working on a multi-wavelength approach, even accurate with disk mass. And because we already knew the stellar parameters from the analysis I just described, we wanted to study the instability of the disk, because our reasoning was, okay, if the disk is unstable, then probably the point here, the key phenomenon is the eruptive accretion. If not, maybe it's class 0, maybe it's something else. So we use the Fecha and Lodato criterion, which is basically, which corresponds to this light blue region. So the symbols are the same, and also we added the orange objects that are class 0 and 1 from the literature. We plot it here, and what we see is that most of the objects, of the young objects, actually lays in here. Not all of them, but a lot of them. So we interpreted this as a possible hint of the fact that more class 1s and 0 that we think actually have experienced or will experience some eruptive event because of the fact that their disk is unstable. This is not like a definitive conclusion, but I think that it suggests that we should always take into account eruptive accretion when we do this kind of analysis. But then, I mean, as I said before, we've got this problem. what is the mechanism that drives accretion? I mean, either it's eruptive or it's steady. What is the physics underneath? And for if we do this for class 2, we've got the viscosity MSD winds provide, and they're both in equilibrium. So if we, the difference is here at the very early stages. And for this reason, because we wanted to populate this plot in this part of the diagram, we study protostars. Because now we do have both the mass accretion rate and the disk mass. And for the first time, we completed this plot. Here, it's the mass accretion rate as a function of disk mass for our class 1 sample. So first, you can see that there is a relation. So this relation is still there only for class 1s. And it's not so like natural because as we said before, the physics of class 1 is different. There is the contribution of the envelope. So it could be perfectly fine if those objects were just randomly put in this diagram. Second, you see an evolutionary trend from like more massive disks and higher mass accretion rate of class 1s to less massive disks and a lower mass accretion rate of class 2. And we're very happy about it. But the point is also that the relations are different. You see here that the slope and the sigma are different within the error of the two populations. So this plot is also suggesting us that those phases, the protostellar 1 and the brimming sequence 1, are different in this space of parameters. Okay. We wanted to study the depletion time. The depletion time can be seen as the time by which the disk is totally dissipated because it accretes material on the star or because some wind. But the ratio between the ejection material and the accreted material is about 100. So we can say that most of the material isn't going to accrete on the central object. And I highlight here this for guys because they do have extremely short depletion time, like shorter than 10 to the 4 years. This is very short, right? Because if the time scales of these objects are 10 to the 4, how they can be like shorter than that? We don't know. We studied a lot of these objects. We have no idea. There are some things that you can take into account, like the uncertainties I told you before, and also the fact that we can improve our the disk mass estimate, but these objects are not like brown dwarf or eruptive stars or strange guys. They're normal class 1s objects. So we've done this. we tried this exercise. We just remove those objects from the sample for a moment, and we try again to fit data. And now magic, the fit of the sample without this low disk mass guys is in agreement with class 2. This is telling us that we should investigate more the low disk class 1's population. Again, we've done this kind of analysis. We overplotted isochrons. Isochrons are defined by the data 2017 as the locus where class 2 evolves. So the point is that thanks to isochrons, you can get the initial conditions of the disk and mass accretion rate. And this is very important because basically the initial condition for class 2 are class 1s, and the initial condition for class 1s are class 0. So if you do this, you can get the initial condition for star and planet formation, because the literature is telling us that planet formation occurs during the protostellar phase. The problem is that isochrones are optimized for classical Qatari stars, so they don't take into account the fact that the envelope is foiling the disk, because as I said before, at the cluster stage, there is no envelope that fits the disk, right? However, if we just forget about this, we say that there is no light trend, okay? The class 1 objects are randomly point on different isochrones with different initial conditions. And why is like that? I don't know, but my opinion is that we are looking to sample composed by objects in multiple star-forming regions. So we're not looking at just a single star-forming region. We're looking at everything which is inside, which is within 500 parsec, and we're trying to do the best that we can. But we're missing information on the environment, and we know that the environment can affect a lot the initial conditions. So I want to stress that we need complete samples of the same star-forming region for both protostars and class 2. So when you review, for example, is a proposal, takes this into account, that it's very, very important for this kind of studies. Okay. Finally, we wanted to test the models. So MHD or MHD wings. So is it the wings that take the material from the outer part of the disk and drive it on the inner part? It's because of the wings that we see this accretion going on, or is because the viscosity of the disk, or it's because basically both of that, and this is like the hybrid model. Okay, those are the lines. And okay, what is your conclusion looking at this plot? Say something. Anything, exactly. Yeah, I agree with you. People try to convince me that the hybrid model will better fit like the evolution from class 1 to class 2, then you still have the low disk class 1s that are not in this framework. And like to me, this is telling us that nothing is working. But I'm not surprised by this, because as I said before, these models are set for classical Qatari stars, and we're looking at different stars. So why we're using those models? Because those are the only models that are available for the moment. So another thing that we'll need is people that do models that describe this protostellar phase. So if you know this topic, if you know people that know this topic, please try to convince them that we need models to compare our data. We are at that stage for which we got more observation data that can describe it. Okay, let's move to the envelope. I will go quicker on this. The point here is that some theoretical works suggest that all I talk about is not really the key point, because most of the material accretes directly from the envelope. I mean, I don't know if it's like that, but the problem here, and this is something that we share in common with people that do high mass formation, that maybe there is a mechanism that we don't know that is able to like accrete material directly from the envelope. This is something that we are not observing. Maybe it's an observational bias, but what we are actually observing is material coming from the envelope to the disk. And thanks to Alma, there are a lot of estimates of this. There are a lot of works. There is actually a review that tells you how much work is doing in this direction. The problem is still is that numbers don't fix the problem. This mass accretion rate is still too low, and also the uncertainties on the mass inflow rate, so how much material came from the envelope to the disk, is even higher than the uncertainty that I got from the mass accretion rate. So there is a lot of work to do. But the question still remains, is the class 0 the stage in which the mass is already set? We don't know the answer to this question. And before drawing conclusion, I would like to do some like watch-outs. Like first, we analyze only loaded sources. So I talked about class 1s, but I should have talked about bright class 1s, okay? Something that is still missing here is dim class 1s that we cannot observe at the moment from ground-based facility. What we need is a complete sample of a single star from region. I would get on for one to start, to see also the environmental framework and to being able to draw a robust conclusion on this topic and to set initial conditions, at least for one star forming region. And then we've done this only for single stars, but we know that more than half of the main sequence stars are in binary system, and that can be true also for protostars and increment sequence stars. So we should also take into account the multiplicity of the systems. Here's a list of the most recent and interesting works that claims this topic. There are also outflows. I only have 45 minutes, so I haven't focused on outflows, but this can be very important to study those objects that are embedded. So we cannot study the material directly accreting, but since we see some outflow, we know that object is accreting because of the outflow, because of the conservation of the angular momentum. And this is amazing. There is also a variability problem. What we have done is just to make a picture, a screenshot of what's happening in a single precise moment. But those objects has variability, like about less than 2 magnitude in the visible wavelength range. So things can be different, and there is also this aspect to take into account. And lastly, this is only for low mass stars. We know that there are eruptives, and there are also high massive stars, more massive stars. So we are far away, unfortunately, to draw the star formation scenario, which is good because it means that there is some work for us to do. Okay, so let me draw the take-home messages, which are a few for the reason that I described before. And those are that the mass accretion rates we observe are larger for younger sources. This is a fact. This is something we demonstrated this. And this is important because we observe these within class 2 at different stages, because MGC 1333 class 2 accretes more than more evolved star forming regions. And it's true between class 1 and class 2. But if we analyze class 1s in different regions, we cannot draw definitely robust conclusions on the behavior, on the relations between the mass accretion rate and the stellar parameters, including the disk mass. Okay, so next steps. On the theoretical side, we need models. I know that Patrick and Bell group in Paris is working on something like this, and maybe in the future there will be some improvement on this. I've been told that is a numerical problem, because the integration time that you need to follow the behavior of a star or population of a star from the core collapse to the class 2 stage it's a lot, but there is room for improvement on this side. On the observational side, we can do a lot of things. I know that we can do a lot of things because this is my field of expertise. Again, we need uniform samples. We need to further investigate the low disk mass regime to see what's going on, to see if the difference in the relation that corresponds to a completely different population for class 1 is just like due to sum of layers, or it's a fact. And in order to do this, we have to do two things: increase the number of observed objects and like focus our attention on low disk mass. Luckily, we managed to get some data, so we're working on this. Stay tuned, because we'll be able to see what is the output, I hope soon. Also, we need to investigate more embedded objects, more embedded class 1s and more embedded like class 0. How to do this? For the moment, we're using only the bracket gamma lines, but there are also other H1 lines. And the idea is to get empirical relations also for the other H1 lines in the near infrared. We're working on doing this with the Penelope dataset, because as you can see here, like the bracket series is something that we actually observe, and we observe these not only for class like normal classical class 1 and class 2, but also for EXors, for FUors, for eruptive objects. So investigating these lines that are usually like forgot, it's very important, okay? And also taking into account always eruptive accretion is always important. But there are, however, objects that continues to be dim in the near infrared part. And what you can do, move toward longer wavelengths, move to the mid-infrared part of the spectrum. There are some attempts of finding relations on the mid-infrared H1 lines. This is the work by Elisabetta Filiación 2015 and Comerano and Fecha 2020. As you can see here, the error bars are very large, right? So, I mean, you can fit this wherever you want. And here, the problem of this work is that the flex calibration was not contemporary, so there is a problem in the variability. So, of course, there are like good works because you have to start somewhere, right? But due to the low uncertainties on this relationship, we cannot use this for the moment to do the same analysis that we've done with bracket gamma. So Alessio Garatti is the PI of an ARIES GTO that we have at INAF, and the idea was that ARIES would observe contemporary to JWST MIRI a sample of class 2 to get these empirical relations. This exercise was successfully only partially because, as you know, MIRI had some problems. So a lot of targets, unfortunately, were not observed at the same time. So we're working on this, but we're not sure that we will be able to provide these empirical relations. We will do our best. Lastly, for doing this, we need new facilities. And I already mentioned MIRI JWST, which is already working. So good, very, very good. But there is also another instrument that is very important for this kind of science, and is ELT METIS. So also ARIES observing the mid-infrared, amazing, but well, it's not enough for the science that we would like to do. The fact that METIS have a coronagraph would be amazing. I mean, the idea by which METIS was developed was because to study planets formation. So if you cover the contribution of the star, you can focus on planets on the disks. But this is also important if you need to identify the contribution of the envelope or the disk. So the idea is to work on two phases, study the envelope, the disk, and then put on also the contribution of the star. And in this way, we will get only the contribution of the star. So the idea is to use the coronagraph 2 times to get information on the star. And yeah, I mean, this is the next step, general conclusive slide. Thanks a lot for your attention, and I welcome any question.
Okay, well, thank you very much, Eleonora. Is there any question here? Maya? If you can say your name, some Eleonora can get to know you.
Again, my you. Thank you very much for this very clear story. I have several questions. The first one, it would be great to have evolutionary track for class 0 from class 1 to start that there are still accreting a lot from the area, which is very difficult to find. But regarding the relation that you have shown between this mass against the accretion velocity,
Stop me when you're happy with the
this one.
this one.
This one.
Okay.
I guess you mentioned that this mass is obtained from ALMA network, but I am really concerned because ALMA many people underestimate mass because they assume that this is optically clear, that the temperature is constant. Can you address this problem?
Yeah. Okay, so those observations, so those estimates of the disk mass were based on band 6, ALMA band 6. And so if you use like the Ansdell model to do this, you basically either set the temperature or change the temperature, but however, you assume that the object is optically thin. And we don't know if this is true for class 1s, and it could be not true. It's also true that by setting the temperature, like I think it's 20 Kelvin, like those objects are supposed to be colder. So people argue that for class 1s you kind of balance, like there is an assumption that will provide you like more massive disk, and another assumption that will provide the other way around. So we argued this. We were not convinced about this, of course, but the point is that we've done two things. First, we asked for band 3. And also for most of these objects, there is also a VLT observation, VLTI observation. So what we're working for the Ophiuchus sample for the low disk mass and contemporary for those objects for which we managed to have band 3 and VLTA is to compute the spectral index in order to know if it's optically thin or thick, and then use the method as a consequence, like if they're optically thin or if they're optically thick. Okay. But this is not what we've done here, and the reason why we didn't have done here is, well, there are two reasons. First, we didn't have enough data for all the sample, and the second was that we wanted to like like to compare to use the same method used for class 2 for class 1s. So here I put like this mass, but this is more or less like the flux, the ALMA flux in band 7 per a certain coefficient, which is the same for class 2 and class 1. So like in the letter we like discuss these as like the relation between the mass accretion rate and the flux of the ALMA band 6. Also to convince people that this is not a good way to discuss estimate. But it's very challenging. But yeah. Maybe that's more important than the radiation from the star at this stage. What we are trying to do, so we discussed these at the Code to Do This conference. I don't know if some of you were there. The problem is that like getting time with ALMA it's very difficult. But and also, I mean, if you ask for this, people tells you, yeah, but you already have this guesstimate, so why you need further bands? And that's something stressful. I don't know. I honestly think that it's easier to go for a large project with Alma, honestly. So I don't know, if you're interested in doing this, we can work together, because I keep, not only me, I mean, all the people that I know, I keep asking for different bands in a single region, and we're not successful.
Is there any other questions here in the room? You have a few, right? Do you want to make another one? Yeah, please go ahead.
I have a concern regarding the accretion rate, because we have derived these parameters from, for instance, gamma, no? Or some transcription is different, but right now the network space telescope is tracing the gamma where you get the ejection. How do you know if this emission is coming from the disk or the regular? It's not in class one, just the regular. Another one.
So for this sample, we checked, because we've got, like, for NGC 1333, we've got a few observations. There were no jets. So I mean, there is no jet. For the other sample, there were no, like, jet tracers. We checked the two mass images to see if we were able to see the presence of a jet. They were not contemporary, so we don't really know. So it could be, but I mean, if those objects are so bright, it means that are very close to the cluster stage. Therefore, it means that it's very unlikely that they have some jets. The more embedded is the source, and the youngest it is, and the higher is the possibility that there is some jets there. And this is why we cannot use this method to study more embedded objects. And this is why we need more lines that trace different things to be able to constrain the things and avoid the contamination, the jets part. But in principle, you don't know. But only, I mean, I would only to stress the fact that, I mean, we use these relations based on the bracket gamma as a constraint. But if you use only the bracket gamma, then you are not able to estimate this, because you have so many free parameters. So you cannot just use empirical relations if you've got your flux calibrated bracket gamma, and this is not going to work. I know, because I mean, people are starting doing this on papers and this.
Yes, now I must ask the streamers from Nando, well, suggesting a command or a president talk. This result fits in the work. So you can estimate well, it's on error, it's something new, but you can estimate the rate of involvement from Nando.
Yeah.
Yeah.
Yeah. So this is something that I personally haven't done, but those people have done it, and I think it's key, because so I focus my work on the mass accretion rate, and this is not enough. We need more material. So the fact that some material is accreting, it's coming from the envelope to the disk. It's important, because it tells you, that there is more fuel on the disk, and it tells you that the instability, the instability of the disk could be affected by this material, right? And again, this is very important, because otherwise we find like a physical mechanism that is able to convert all the material that is coming from the info to the star. Or, we have to accept that the eruptive accretion is not something uncommon. And people are not convinced about it, but I don't know. We have to demonstrate this. Also, I mean, they find streamers on class 2. And this is weird because I mean we all the paradigm that we built says that the envelope is dissipated on class 2, and we can forget about envelope on class 2. But this is not what ALMA is telling us. Of course, we need statistics, but this is interesting because like if there is still envelope accreting the disk on class 2 stage, this, I mean, at least says 2 things. First, that the models that we are using are completely wrong, and they don't even describe the class 2 evolution. And second, that class 2 and class 1 are more alike than we think, because this mechanism is still going on also on classical sitar stage. That's very interesting. Sorry? Yeah, I mean, one of the possible like description of the eruptive accretion is the instability of the disk. So basically, when the disk is more massive than like self-gravity, that can be because of self-gravitating, it produces this strong burst that should follow magnetic lines if there are if the magnetic field of this forming star is already formed and intense. What we don't know during the class 0 stage if the magnetic field at that stage is already formed, is it polar, is strong enough. People are starting doing this kind of research like now.
Okay, perhaps we can close the beginning.
I am Eleonora. Thank you for the talk. It was very clear. So I have a comment. You say that the key of everything seems to be to work on the same star forming region. But I have some concerns about this because in this 1333, the region you mentioned, there is a large diversity of objects. So I have studied for religion for a while, and I cannot see 2 identical objects. So the objects probably have similar ranges, but one had the bigger bead, or the ones have spirals, or the other had very compact beads, ones had very powerful outflows, even very powerful chemical objects, or the yet, so I always prefer the study in deep of the objects rather than statistical of many objects that have not been studied in deep. So, well, this is my opinion. You comment, maybe you want to comment more on that.
So it's just based on my personal experience. Like during my PhD, I work with very different groups. One both based in Rome, one was focused on a statistical approach with inertial data and like cover all the galaxy and do these things on large scale, right? Earth gold belt, but large numbers. Saying that going and studying little objects didn't give you information on the general picture. And then I work with another group led by Brunella Nicini that does what you're saying, take an object and study everything of the stellar parameters, detail, mass accretion rate, outflow, every tracer, a multi-wavelength approach on that. And it says that in this way we can establish something, otherwise if we go for a statistical approach, we're losing information. I personally think that, I mean, why we do science? Because we've got a question and we want to answer that question. So if the question is what's going on in that star, we go and look at the star. If the question is what is the physical mechanism that drives material coming from the outer part to the inner part, I mean, we have to go for a statistical approach. It's not like the one is better than another one. Everything depends on your scientific question. So what is your scientific question? You said it, and you like compute all your observational proposal and everything. I personally don't like when in a proposal they say, yeah, but by studying this first, I want to answer this fundamental question of the physics. You can, you cannot say this by only studying one object. But if you say this object is strange because it's doing something that we don't understand, so I want to observe it, yeah, of course you should got the data. So it depends on, I personally think that it depends on your scientific question.
I disagree with the sentence you say, because in my opinion, if you want to do physics, you have to do physics. Otherwise, if you are doing statistics, you are doing mathematics, which is different. So my point is that if you want to understand the physics, you have to study and several objects in it. So you know the mechanisms that are working on. And then once you know the mechanisms, or when you know how to calculate the mass of the disk, when you know how to estimate the age of the object, when you know this, how to do this, then you can do this for a large sample, and then to draw additional information on the statistical properties. But what I am emphasizing always, also, is to reverse the project, the problem, no? You have to do the statistic later, not the statistic first, with, for example, full calculation of the mass of the disk, because you got some strange results sometimes. I remember a couple of years ago, I was talking with Pedro. He told me, well, we are doing something wrong because we see that the EXors stars, the mass of the planets is larger than the mass of the disk of the object. But no, you are not doing things wrong. It's the people that is calculating the mass of the disk, assuming that the emission is optical, is doing something wrong. So you better last this, most of the emission is optical, so the mass you obtain is 90% correct. But if you have an EXors star, for example, where the disks are smaller, the central region is denser, and you make a big error, assuming, for example, that the emission is optical.
Yeah, but
and this can then give contradiction. Okay, so it's maybe a philosophical approach, but I think there is a problem here in some cases.
yeah, and I mean, as long as you describe what have you done and people can reproduce what you're doing, I think it's fine, you're doing science. The problem is that when you publish a paper and people don't have access to the data and cannot reproduce and just have to trust you, that's a problem, right? I don't feel we're fair. We do the best that we can with the data that we have in the end.
Okay, I think we have to close that. I think it's a very nice discussion, philosophical discussion, but I think we need to leave it here. And maybe discuss after one object versus a systematic approach. And I think this is open. I don't think we're going to find the answer here. But before we close, two announcements. First, we're going for lunch now. So whoever wants to join us, we're going to groups, places, somebody place around the corner. And the second announcement is that Eleonora will be here today and tomorrow. And tomorrow I have organized a session because Eleonora, for a great scientist, she's also very active in the gender equality community. And tomorrow I have asked her kindly, she has accepted that she tell us very informally what she does, what she has been involved, because I